Hey everyone, welcome to another problem session. This one will be very quick and just don't have a lot of time these days. Okay, so this is a problem from OpenStax. That's my book, and an earlier version of this book, is in here. So if you want to go there, that's fine too. Okay, this would be a place you would go. If you like my explanations and things like that, my problem choices, I like to pick some challenging problems for introductory physics. Okay, you would want to do some of the more elementary problems either in here or go to the OpenStax. Okay, if you like my channel, please subscribe to this channel. It helps grow the channel. If you like my explanation, hit like button. Okay, so that's enough for advertisement for these things. Let's look at a problem. This is a pretty good problem actually. This is 4 ohm, 8 ohm, 4 ohm. Okay, so this is very simple circuit. There is solenoid here and there is solenoid here, and each of these is changing in strength. So like dB1 dt is 50 Tesla per second, but the direction is coming out, so it's getting stronger coming out, magnetic field, and this one direction is going in, and dB2 has the same magnitude. So this is just the magnitude part. But direction remains. Direction here is coming out and direction here is going in, as indicated in the figure. So it will, if you don't change magnetic field, there will be no current. Okay, so if dB1 dt is 0 and dB2 dt is 0 in this situation, then no current induced. So this is really classic Faraday law. So you can actually, in Faraday, you can pick any loop and you can tell what's going to happen in that loop. So let's pick this loop. So in that loop, if the magnetic field is coming towards us and it's increasing, then EMF will be induced, like the back EMF, right? So it will be induced to go in. So EMF will be induced. So there will be EMF induced. So EMF induced, and its orientation will be like this. So it's going to be current will be going down here. Current going down. So let's call this the current in here. We'll call it I. Okay, I1. And of course, it's not the same because this current here through 8, there will be current from this other loop as well. So now we do the same thing in this one. Now it's going in. So X means magnetic field is going in and is increasing. That means the back EMF will be such that this magnetic field will be coming out like that. So I use right hand rule. So the back EMF will go this way. And so it will be such that the current will be going that way. So we can think of this effectively. We can make another circuit just so we can just forget this. I have a circuit with some EMF this, which is equal to, so EMF induced 1, and this is EMF induced 2. So EMF 1, and we'll calculate what the EMF 1 is, and then the other one is is and this is EMF2. Now if this B was more not constantly changing, it was changing, so the sign could also change like this. You could have like a 5 cosine 10t, something like that. Then the direction will also be changing. So, but this is not the case here. We could handle that also, but its problem is very simple. Okay, so this is the problem, and the current here is I1, and the current here is I2. And so you can see that in this over here, I1 and I2 will come in. So over there is I1 plus I2 in the same direction. So it's gonna, so this is, I don't need to write something new. And so what's the E1? E1 will be equal to d phi, like phi of 1 dt, absolute rule I'm using, and this is the area of this times the magnetic field over rate at which magnetic field changes. So this will be area of that A1 and dB1 dt. And what's the area 1? Where pi, it's a radius of the solenoid is 0.1 meter, 0.1 square, and this is 50. So this is, now this is meter square, and this is Tesla over second. Now this looks like a very complicated unit, but once all of this said and done, it will be a volt. This whole thing will turn out to be a volt. I don't want to really go out and relate all of them and get to the volt, but you know EMF will have E dot dl, and electric field times distance will have voltage, right? So that's the unit will be volt. E2 will be carrying out the same way, pi 0.2 square times 50 volt. So we just see E1, E2, and in the end you can put the numbers in. You can see that here I can do maybe a loop equation. So you start from here, so jump E1. So this is like Kirchhoff voltage loop, you know. So and go over. This is this is going to be minus I1 plus I2 times 8, and then I go through here, minus I1 times 4. So this is IR, this is the current, and this is the resistance. This is the current, this is the resistance, equal to 0. I came back to the same place. I start from A and come back to the same place, and I do same thing for this guy. Let's see, start from here. This is going to be minus E2. Okay. I'm going against it, so I'm going to have a plus I2 times 4, and then I'm going against this current. Current is going this way, but the green thing, the loop, KVL loop, is going the opposite direction, so I'm going to be plus I1 plus I2 times 8 equal to 0. So this is 12 I1 minus 8 I2 equals E1, and this is 8 I1 plus 12 I2, because send this on the other side, E2. So let's see, I send these guys on the side, so this is the case. Okay, so you can see I can multiply this by 12, multiply this by 8, and then add. That thing will kill this guy, and so you have a 12 times 12 is 144, plus 8 times 64, that's I1, 12E1 plus 8E2. So you can see here, this is the only difference. So this is going to be 4 times E1. So this is actually, don't have to go E1 into separately, just the same. So in terms of 4 times, right? So this is 32 plus this 44 E1. So I1, I got 44 E1 over 4 and 4, 8. This is 200. So this is the answer for I1. And I can, of course, put in there and carry out the numerical value, which I'll leave to you. And to get I2, just plug in there, or we can do it more or less the same way, plug in, or you can do multiply this with 8. So let's multiply this by 8. So over here, and multiply this by 12, and then subtract. That will get rid of this guy. And so if I subtract, I'm going to minus here. So minus 64, and so it's going to be all of this 208 I2, and I got 8E1 minus 12E2, and E2 is 4 times E1, so this is 48E1. So I2 is, you can see this will be 40 over 208 E1. Okay, so I hope I didn't make some numerical mistake, but the upshot is in a very simple circuit, if the magnetic field, if its circuit is bathed in magnetic field and magnetic field is changing, then you will have induced EMF, and induced EMF will drive the current, and it's not very difficult to set it up. And many times in the questions, these simple circuits show up. So hopefully this is helpful to you. That's all for now. I'll see you in another video. Bye.